In this particular video, my goal here is to give a crash course on dealing with some light problems, converting nanometers to meters, and using the light equations C equals lambda nu and E equals h nu. My chemistry students should have been in class when we discussed following notes on light spectrum, and so we talked about the wave equation, C equals lambda nu, and so you should be familiar with the speed of light is c, and the wavelength has to be measured in meters. Frequency is this Greek letter nu, which in chemistry is denoted with the letter that looks like a V. Greek letter nu, Nu. In physics, it'd be an F, which makes a lot more sense, but in chemistry, they use F for something else, and so can't use it again, I guess. Otherwise, I guess they think you're confused. We talked about converting wavelengths, and so you've probably been through these things. My idea here is that nano stands for 1e minus 9, and so when I'm converting nanometers to meters, if it says 453 nanometers, I just get rid of the n and put an e minus 9 on the back, and boom, it's in meters. It's a piece of cake. You can, of course, go to your normal old conversion factors, and you got nanometers on the outside, so nanometers to the bottom, meters on top. 1 meter is equal to 1 billion nanometers. You set it up and you divide it. Now, 453 times 10 to the minus 9th is the same thing as 4.53 times 10 to the minus 7th. It's just a matter of how you put that decimal point on there. Your calculator will always give you this final answer over here, but this answer that I have here isn't wrong. So if I'm doing 764 nanometers, I just give it to the n, put an e minus 9 on the end, boom, you're done. If you don't understand that, you need some more work with it, just always go to your conversion factor method, and it'll be fine. Meters to nanometers, and that's what this should read up here, meters to nanometers, not that way. I just try, if it's easy to do, I just try to make this e minus number equal to e minus 9, and so move the decimal to the right to get an e minus 9, and so that would be written as 223 times 10 to the minus 9th, and then e minus 9 means nano, and so that's 223 nanometers. So on this bottom one, it's e minus 6, so we would have to move that to the right 3 times, and so move that to the right 3 times, we get 12.3, 123, and then finally 1,223 times 10 to the minus 9th, which is going to be this. So 1,230, and that would be 1,230 nanometers. If you get confused, just do your standard old conversion factor and put meters to the bottom and nanometers on top, 1 meter at the bottom, a billion on top. All right. We've worked through these right here, and I'm just going to skip through this because it should have it. We've talked about this example right here, the light spectrum. Energy of a photon, energy is equal to Planck's constant times the frequency, h nu. And we worked through a problem like that, and so there that is. And now you probably want to see some sample problems on the particular worksheet that we had assigned. So let's take a look at some different ones here. So here's some conversion problems, and the one I picked to do is this 777 nanometers. And so to me, that's really easy to get into meters. I just do 777 e minus 9, and I'm done. But I want to show you the conversion factor method, the proper way to do it. Nanometers go to the bottom, and meters go on top, and a billion goes with nanometers, and 1 goes with meter, because 1 meter is a billion nanometers. And you would get 7.77 times 10 to the minus 7th, and there it is up here. Now, I would have just written 777 e minus 9, and that's the same thing. It's the same number. If I want to do meters to nanometers, meters to the bottom, nanometers on top, 5.7 meters, how many nanometers is it? Well, if you've got 1 meter, you've got a billion nanometers. If you got 2 meters, you have 2 billion nanometers. If you have 3 meters, you have 3 billion nanometers. And if you have 5.7 meters, you have 5.7 billion nanometers. And so that goes right there. All right, so hopefully you can work your way through this and ask questions if you have any on conversions. Let's apply some of the formulas at this point. So let's take a look at one of these sample problems. This is on the worksheet. This is number 2. I think this is the 3rd problem in number 2. A microwave has an energy of 4.092 times 10 to the minus 24th joules. And again, if you're not in my class, I always use E notation like your calculator does, because your calculator would, of course, use the EE key. I'm typing that in here right now into the calculator. And so when you're calculating them, you type and use that EE key. If you're not familiar with the EE key, I think you should get familiar with it, because, man, it really saves you a lot of the times when you're doing your calculations, especially when you're dividing. It gets very tricky. You have to be careful with parentheses if you don't use the EE key. But if you use the EE key, you don't have to worry about it. Find the wavelength of the photon. Well, I've got my information over here. I've got the energy written down. I've got the formulas, and I've got the constants in here. And there is no way, using these formulas, to directly calculate the wavelength from the energy. Yeah, I could combine these two formulas and get a larger formula, but I'm not going to do that. I'm going to do this as a two-step problem. And so the first thing I'm going to do here, I'm going to use the energy, and I'm going to find the frequency, because I got E equals HV. And I know the energy, and I know Planck's constant. And so the energy is this 4.092 times 10 to the minus 24th. That has to equal Planck's constant H, which I'm just going to use 6.6 times 10 to the minus 34th, times the frequency, nu. All right, so how do we solve for nu? Well, we're going to have to divide the 6.6 over. And so 4.092 E20 minus 24 divided by Planck's constant, it's going to equal nu. And if you plug that into your calculator, which I'll do right now, here's my calculator. So I got it divided by 6.6. Using your EE key, E minus 34. And you should get a value of about 6.2 times 10 to the 9th. And so that's what I got recorded there, 6.2 times 10 to the 9th hertz. Well, now that I know the frequency of this, now I can use C equals lambda nu, and I can figure out what the wavelength is. So the second step here, I'm going to use C equals lambda nu. I know the speed of light is 3 times 10 to the 8th meters per second, and that equals the wavelength in meters times the frequency in hertz. And so I'm going to have to divide the frequency in hertz over 3 times 10 to the 8th divided by 6.02 E9. And so I've already got the 6.02 E9 in there, so all I have to do is do 3 EE. I just realized now the calculator's on here, so we'll move it up here a little bit. 8 divided by my previous answer. And I get 4.8 times 10 to the minus second. My mode right now is in scientific mode, so if I take it out of scientific mode, you wouldn't get that answer on your calculator. You would get the decimal equivalent of that. And that was a mistake here. I didn't want to divide by the answer. Give me 1 second. 3.8. Sorry, 3E8. And divide by 6.2 E9. That's what that was, right? Yeah. Okay. And your calculator will give you 0.048 meters. That's roughly 5 centimeters. That's a microwave. I think that's pretty reasonable. I mean, I'm not super familiar in the everyday life of microwave sizes. So you could write 0.048 or 4.8 times 10 to the minus second. Again, I was in scientific notation here, so whichever way you like to write that. So two-step problem using both of these equations. If you have questions in your class, you can ask me. Let's take a look at the bottom of the worksheet where I got this data table. And on the data table, we got a bunch of things going on here. I got a column for color. I've got a column for wavelength, frequency, energy, etc. Now up here at the top, I've written in some stuff up here to help you. To get wavelength, the only formula that has wavelength in it is C equals lambda nu. So to figure out the wavelength, I'm going to have to use that formula. And over at the end, the only formula that has energy in it is E equals H nu. And so if I ever need to calculate the energy, I need to use that. Now the middle one, I could use either one, depending on what information I have been given at the particular time. So our first one here, the only piece of information I have is a wavelength of 412 nanometers. All right. So the first thing I need to do is I need to take that 412 nanometers and convert it into meters, because using nanometers isn't useful for us in this formula because this speed of light is in meters per second. So I need to have the wavelength in meters, not nanometers, because I need my units to jive. So I'm going to use C equals lambda nu here, and I've got 3 times 10 to the 8th. I'm going to convert the 412 nanometers into meters by just sticking a 412 e minus 9 on there. Boom. I'm already now in nanometers, and that's times nu. So here's my basic setup. If I bring my calculator in here, and I want to calculate, that would be 3 E8. I'm going to divide by 412 E negative 9. And I get a frequency of 7.3 times 10 to the 14th hertz. So there my frequency is calculated. Now, what about energy? Well, energy is just H times nu, and so I've already gotten my frequency here, so I might as well just multiply it by Planck's constant. And Planck's constant is 6.6, as we saw in the last slide, E minus 34. And we get an energy of 4.8 times 10 to the minus 19th joules. And so that's that answer there. Now, what about the first column? How do you determine the color? Well, the color, as you can see here, it says see page 98 for your textbook. So if you're in class, we have a textbook in class. It's the digital version posted on Teams. You turn to page 98, and there's a chart that looks a lot like this. And so this is just one I found on the internet here. And this particular chart, what you need is you need the visible spectrum with some wavelengths, and this one's in nanometers. So there's 400 nanometers, and so we're interested in 412 nanometers. So 412 nanometers is rather close here, so it looks like it's still going to be in the violet region. So this color of light is probably violet. Now, we could have started off from there, from the 412. So like on the 625, you go here, there's 600, and 625 looks like it's going to be in this range right here. So maybe orange, I don't know. Probably. So there's your answers to this one. There's your example problems. So if I'm doing my next one, I've been given energy. So I'm going to use the E equals H nu. I'm going to figure out the frequency. Once I know the frequency, I can go over here and figure out what the wavelength is and put in the wavelength. Put that in nanometers. Since these are all going to be visible light, they're going to be somewhere between 400 and, I don't know, 800 nanometers. So those are your nanometer answers. Just got to fit them in exactly. And then your colors should come off of the chart. I did the calculation. I didn't show you the work down here. There's some actual, I thought I had some problems down here. Maybe I don't. There they are. So here's the problem that I did to calculate that one. E is equal to H times nu. There's nu right in there. And I should have showed you that before I did that. The Smart Notebook watermark is really getting in my way. So, all right. If you have any questions in your own class, feel free to ask in class. Thank you very much. Have a good day.